so we need to explain how the optimal flow velocity for water in a pipe has consistently been approximately 2 meters a second over 100 years. In order to do that, we need to mess around with this expression a bit. So we need to eventually come across the optimal velocity, right? In order to do that, first we need to recognize that the mass flow rate is the only non-constant variable. And so mass flow rate is just equal to the density times this by the cross-sectional area of the pipe, which is just pi times d squared over 4, times this by meters per second, the velocity. And so here we have the velocity, right? And we're trying to find the optimal velocity. So we need to then isolate this variable. V will be equal to 4 times the mass flow rate over rho pi d squared. And to make our lives easier, we can actually change this expression to be equal to v squared. And so we'll just need to square both sides of this expression. So we get v squared over 16 mass flow rate squared, rho squared, pi squared, d to the 4th. So by doing a little substitution, we get a new expression, capital cos times diameter times this by length plus PC times this by mass flow rate, friction factor, length over diameter is where we start substituting, v squared over 2, so v squared is equal to this, so 16 over 2 just be 8, and then just substitute everything else like normal. Mass flow rate squared, density squared, pi squared, and then d to the 4th. Okay, from here we need to find the optimal diameter for whatever mass flow rate that we desire. So to do that, we'll set a derivative for AC with respect to the diameter. And so we can start writing the equation down and then start multiplying values by each other. You got 8 mass flow rate cubed times this by the friction factor times by L times this by PC. Make sure I did it right. Yeah. Yes. Yeah. And then all this over by rho squared, pi squared, and then d to the 4th times this by another d, which is d to the 5th. But since we're deriving in terms of d, that'll actually be -5 over d to the 6th. So this will be our new expression, and we set this equal to 0. Okay? And so we're going to simplify it a little more here. We'll just put that in between. So we do this, -5 times 8, we'll get -40. Mass flow rate cubed, friction factor, length, times this by PC. All of this over rho squared, pi squared, d to the 6th is equal to 0. And from here, we can move this second part of the equation over to the other side. Sorry. All of this over rho squared, pi squared, d to the 6th. So I'm actually going to multiply or actually switch these two in their places. So you can get rho squared, pi squared, d to the 6th, and then that'll just swap places with the left side of the equation. Just got to rewrite this again. PC over C times L And so now we need to isolate D and also get rid of this sixth power. So to do that, we're gonna take these two variables and move them to the other side again. And doing that, you'll get 40 friction factor times L times PC over CC times L, but you'll notice that the L's do cancel out. I just noticed that. So no need to worry about the L's anymore. Messing up my actions right here. So you'll get 40 friction factor PC, wrong color, PC over CC, right? Yeah, and this CC is multiplied by P squared times by pi squared, and then all of this times by the mass flow rate cubed. The reason why I put it on the outside is because we still need to worry about the sixth power, and what we do is we can raise this entire quantity to the 1/6 power, and here, since it's already to the third power, the power on this will just be 1/2, which is basically just the square root. And this here is the expression for the optimal diameter. So now that we've found the optimal diameter, we can find the optimal velocity. So the optimal velocity, the equation for it, based off of the equation we found earlier, so that would be 4 times the mass flow rate over rho times pi and d squared. And so we found that d squared is equal to this. So we need to square this value. And so we square the m to the 1/2 power, you will just get m, and since it will be in the diameter, the m's will actually cancel out. So we can just get rid of the mass flow rates, because of course they cancel. This one, we will multiply the 1/6 by 2. This part of the equation will be to the 1/3 now. Now since this is in the diameter, we can actually flip the diameter in the numerator, and this right here will be the expression for the optimal velocity. So the question asked how could be that the optimal flow velocity for water in a pipe has consistently been approximately 2 meters per second over 100 years. And people ask that because obviously costs do change, but we need to remember that the capital cost will increase, yes, over the years, but so will the power costs, and they actually increase in the same proportions. So like power costs 1 to 1/2 years later, it may increase by by a factor of 2, but so will the power costs, and these are the same ratio. Just keep going on and on and on and on and on. But no matter what, power cost, or the capital cost and the power cost, will create the same ratio no matter how long it's been. And so in turn, they'll basically cancel each other out, and these factors are all constant, right? Because of that, the optimal flow velocity will stay consistent. Like they stay a consistent 2 meters per second over 100 years. So I'll even write it down. So the power cost and the capital cost will stay the same ratio. Stays as the same ratio. And so the optimal flow velocity will stay the same even after a long period of time.